Hello, I am Thomas Wesley Holmes. Currently, all commercially available CT systems can utilize energy integrating detectors EID at a standard image spatial resolution SR of 1/2 a millimeter cubed. As new advances in CT technology have been developed, both EID and now photon-counting detectors, PCD, have the capability of creating images at an ultra-high image spatial resolution, UHR, of 1/4 millimeter cubed. This improvement in the spatial resolution of new UHR CT imaging systems that have a smaller native image voxel size, blooming artifacts, and partial volume effects are expected to be reduced. The purpose of this study was to explore the image quality improvements of UHR CT and calcified plaque imaging. To get a better understanding on the impact of blooming and partial volume artifacts, images of the same object were taken with SR and UHR for comparison. On the left, we can see each of the two scans from UHR and SR of calcium inserts with the same attenuation and 3 different diameters in a cardiac phantom. A line was created through the center of the 5 millimeter insert for both resolutions, and their corresponding profiles are seen in the figure on the right. Here we can see the blooming and partial volume artifacts noted by the arrows, which cause the CT numbers of the plaque to be underestimated and its apparent width to be overestimated at the 130 HU threshold, which is traditionally used in calcium scoring. Our methods for image acquisition and reconstruction included 7 excised human hearts, 5 male, 2 female, ranging in age from 54 to 72 years. SR and UHR images were acquired with EID-CT and UHR beam blocking cones. The scan parameters were 120 kVp, 211 MAS with 1 second gantry rotation time. The image reconstruction kernel for the SR was a UQ36 and for UHR was a UQ77. Emory CACS was also used, and it is an in-house coronary artery calcium scoring toolbox. The same lesions were selected in the SR images and the UHR images, and it calculated the volumes and Agatston scores. The multi-resolution image representation is a fusion algorithm of both SR and UHR images. Smooth soft tissue features from the SR were included, and sharp calcified plaque features from the UHR were included. A mask was created by thresholding, and a soft mask used a series of morphological operations to create a final image that blends the UHR and SR images. 105 unique calcified plaques were found within the 7 excised hearts. Here we see the regression plot for the calculated volumes. The SR values were placed along the x-axis and the UHR values along the y-axis. The UHR calcium volumes were 67% of the SR measurements and in good agreement with an R-squared of 0.81. This trend demonstrates that the SR images overestimated the volumes of the plaques due to the blooming and partial volume artifacts. This figure is the regression plot of the calculated Agatston scores. The UHR Agatston scores were 59% of the SR measurements and also had a good agreement with an R-squared of 0.81. This trend also demonstrates the effects of blooming and partial volume artifacts. Additionally, we found 4 plaques that had dense calcifications with voxels that have a CT number greater than 1,000 in the SR images, whereas in the UHR images, 102 plaques contained dense calcifications. Our proposed multi-resolution images are a representation of the UHR and SR images in which the calcified plaques from UHR are inlaid onto the standard resolution soft tissue images. This process is comprised of a soft kernel being applied to the SR and UHR images and then inlaying the calcified plaques based on a threshold mask. This figure demonstrates the SR, UHR, and blended resolution inlay images at 4 different axial slices of the same excised heart. The SR image on the left shows the soft tissues well, but the calcifications are blurred from the blooming and partial volume artifacts. The UHR image in the middle has a lot of high frequency noise in the soft tissues, but has a much sharper representation of the calcifications. The blended resolution inlay image on the right incorporates the soft tissues from the SR and the plaques from the UHR, producing a unique representation of the feature space. Here we are demonstrating a zoomed in view of the plaques from the previous figure at a wider window level. This different representation of the same plaques demonstrates the variability of impact on visualization from the blooming and volume artifacts, which is significantly reduced in the UHR and multi-resolution images. The blended inlay images have retained some of the sharp edges and noise texture from the UHR image around the plaques, while still smoothing some of the noise by incorporating the SR image. So calcium scoring metrics seem to be overestimated in standard resolution CT scans compared to ultra-high resolution CT scans. This is seen in that the volume was 33% larger and the Agatston scores were 41% larger. This trend is directly attributed to the blooming and partial volume artifacts found in the SR images. CAC scans are low radiation dose and relatively noisy. This then causes the UHR acquisition to amplify high-frequency noise in the images. Here we proposed a multi-resolution representation of the UHR images in which the calcified plaques in UHR are inlaid onto the standard resolution soft tissue images. This is still a work in progress, and more advanced calcium scoring metrics should be developed to take advantage of the UHR features. Some of the limitations of the study include that there was no cardiac motion. Additionally, there is a lack of widespread availability of UHR CT systems, as there are only 2 FDA-approved systems installed in the US. Thank you.